So hi everyone, welcome to the second New York Haskell meetup. It's a great crowd just like last time. Thank everyone for coming. It was a great holiday party yesterday. Just want to make two quick pitches. First is we've got a great crowd, but there's room for more. So if you know people that would be interested in coming, publicity is great. We want to promote our great language. Number two, we're lining up a lot of good talks, but it's always good to have as many talks as possible lined up. So if you are interested in giving a talk, be it a small talk, a long talk, on just a little project you did, or a more sort of lengthy presentation, talk to myself. That's Rick Meinrich in the back there. He's one of the organizers of the Haskell meetup as well. Doug up here, if you want to stand up and wave hi so people know who the organizers are, who they can talk to about whatever they want. Ryan is somewhere, and yes, and that's 1, 2, 3, 4. Am I forgetting? Oz, but he's not here. Is he here tonight? Okay, so those are the organizers. Come talk to us if you want to present or about anything else. And now I'm going to introduce Edward Kmet, who is a coworker of mine at Standard & Poor Capital IQ. He's written a zillion and one libraries, and he discovered with the Lens library that if he added documentation, and then he got a lot more users. So this is actually rapidly acquiring a reputation and finding widespread use, and it's really cool. So he's going to tell us all about it. Thank you, Ed.
So I'm going to waffle back and forth between some slides that I have that have a lot of the theory and the motivation, like from a technical standpoint for lenses, and just like a GHAI session where I'll use them in practice, so that even if you're having trouble following along with the theory and the derivation, you can see them used and get a feel for how you use them in your own Haskell code. All right? I've got a lot of material to cover today, so I'm going to ramble on for a couple hours. I apologize. So I guess the first question is what is a lens? So in imperative code, you can very easily read and write to like nested getters and setters, like way down in a hierarchy. I can call foo.bar.baz.collects and plus equals 10, and I don't really think too hard about violating, I guess, what the Eiffel guys call the law of Demeter, and going down and accessing properties of properties of properties. In a functional setting, it's a lot harder to do that though, because I have to use record syntax, and I have to go in and it costs me more and more because I have to keep talking about the same object to go deeper and deeper. So record updates are not very compositional. And so PLT Borat, based on actually I think a version of a talk Tony gave on lenses, Tony Morris, said something to the effect that co-state comonad coalgebras are the equivalent of Java member variable update technology for Haskell, and that is really what, if you take nothing else away from what a lens is, it's getters and setters. We just smash them together into some kind of objects. So a simplest form of a lens that we might make would be to pair the getter, let's call it view here, with a setter. So we'll get an A out of an S, and we'll set taking an S and a new A that we want to replace into it, and we'll give you a new S. Okay, and we want to put some common sense laws on these. Okay, we can actually derive these laws about 4 or 5 different ways, and they all give you the same laws, so that kind of gives us a hint that we're onto the right abstraction. And one is that if I get something out of my hole and I put it back, it's the same as if I didn't do anything. So a lens has no other effects, right? It doesn't bump a counter somewhere inside the object. It doesn't do anything like that. All it can do is read and write to a part of it. And if I put something in, I have to be able to get it back out. Okay? And then finally, if I set twice, if I set it to something and then I set it to something else, it's just like I did the second setting. The first setting didn't matter. Okay? So these 3 laws let us reason about code that uses lenses. Okay? And this is if I give an answer on Stack Overflow that goes on for hundreds of lines about this, using this exact formulation of lenses. We're not going to be using this kind of lens today. It goes so far and then stops. Okay. So to talk about that co-state, comonad, coalgebra, just long enough to throw it away. So what that means is that if we were to take this definition, they both start with an S. And so I could theoretically just fuse these two functions together into one function. I give you a function that gives back a pair of the A to S and the A. Right? And that construction on the end happens to be the store comonad or the co-state comonad, if you want to go about it from a theoretical perspective. And this is a store comonad coalgebra. And the laws to be a comonad coalgebra in this case are exactly the lens laws that we just stated. Okay, so that's a completely different way that you can get to the exact same laws. I think that the common sense version makes more sense. This one is also, this is the approach that I used in my Data-Lens library. That was the lens library that I used to sell everybody before this one. I handed off maintainership on that, and then I subsequently stabbed poor Russell in the back by writing a new lens library. So, I mean, this is like if we were to look at the version inside of Data.Lens, the only reason I wanted to point to this is that you can build a category for these, where you can compose these. And there's the category class basically says that you have dot, which lets you compose things kind of like functions. You can compose arrows in the category, and that there's an identity arrow for every object in the category. There will not be a test on this code. We're not going to use it. The problem with this approach is that somebody has to remember to import control.category. They have to hide a couple things from the prelude. What I want to do is I want to write lenses that I don't need to go off the control.category and grab dot from. And along the way, we're going to get some extra stuff for free. Okay. I was holding this up kind of as a straw man. All right. So there is a, this is a reference to a talk that was given by Eric Meyer probably 10 years ago on a bunch of language features that eventually became linked inside of C#. In Haskell, we often have, there's an idiom that we use over and over again. That you'll see in certain people's code. That is like, if we start with like say dot here, I can work with dot, dot, dot. Okay? And now instead like dot goes into a function of one argument. Dot, dot, dot will go into two functions deep. Right? Dot, 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 dot. We'll go three functions deep. As many dots as I compose here, I'm gonna nest that many arguments into a function. Okay, this is I believe Connell Elliott called them semantic editor combinators. He gave them all sorts of fancy names. We can do this with fmap instead of functions, because the definition of fmap for the function functor, the function from A or whatever, is fmap, or fmap is dot. We can generalize this pattern and say, well, I can go instead of going fmap where I go under one functor, I can go under two or three just by using fmap.fmap or fmap.fmap.fmap. Okay? Interestingly, the order of these arguments is kind of reversed from what you expect, because I'm taking a function from A to B to a function from f of A to f of B. Let's go here. A function from A to B to a function from f of A to f of B. And so each one of these is, the dot is actually reading backwards from the way you would come at it from a Haskell perspective. You'd think about it from a Haskell perspective usually. So these are semantic editor combinators, and Connell gave these all sorts of fun names. We had like result was dot, and element was fmap, and second, and you can compose element.result.second, and walk down in for editing assignments and whatnot. I'm going to make an alias for this, just so for sake of discussion, because this is going to be the same pattern for aliases that I'm going to use for the kinds of lenses that I want. Okay? And so a semantic editor combinator is going to say, given an S and a function from A to B, I can give you a T. So this is like fmap, right? If this was f of A and this was f of B, this would be the signature of fmap. Right? But also fmap.fmap fits this pattern, because I didn't actually prejudge that this had the shape fa. S could be lots of different things. Okay, so fmap.fmap is a semantic editor combinator. And fmap.fmap.fmap, or result.element.second.first. All of these would be valid semantic editor combinators. And if we look at fmap, fmap is then a semantic editor combinator that says, given an f of A and a function from A to B, I can give you an f of B. We can just put a different signature on it. Right, because this expands to the existing definition of fmap, or the existing signature. And then first, we'll walk over the first element of a pair, which this guy is obviously not a functor in capital F sense of functor, but it still has that same kind of functoriality of it. It's just the functor over the first half of a pair. Given a pair of A and C, and a function from A to B, I can give you a pair of B and C. Okay. So this leads us to the first construction that we're going to deal with in the lens library that is not a lens. We'll talk about setters. So the same way that we can compose dots in series, or we can compose fmaps in series. These are idioms that a lot of people know in the Haskell world. These get used a fair bit in real production code. A less known idiom is that you can compose traversable functors the same way here. How many people here are familiar with Data.Traversable? So I have some idea. Okay. How many familiar are with like mapm? All right. So traverse is like a generalized mapm. Applicative is slightly weaker than a monad. Okay. With an applicative, you don't get you only get the there's a combinator app or lift A2 or whatever. You can use that as instead of bind. So you don't have all the power to choose the next calculation based on what values you've gotten out before, but you can still stitch together applicative results. Okay. And traverse looks like this. It says, given a function from A to B that has applicative side effects in M, I can take an f of A and give you an m of f of B. Okay? If this was map M, this would be a monad M instead of applicative. And if it's map M out of control.monad, it'd probably have list here instead of that. So the traversable class says, I don't care what kind of applicative you give me. You give me an applicative, I will walk through my my F and find all of the A's in it, turn them into B's, and give you back an F of B. Okay. But if you look at the signature here, we can compose this. Traverse.traverse looks a lot like traverse. Just in the same way that fmap.fmap looked kind of like fmap. I just now have f of g of a. And I'm not bolting like a compose new type in here to make this really painful and to work with. Here, traverse.traverse, I'm now saying if you give me an f of g of a, I'll go in there, I'll go into the f, find all the g of a's. I'll go into the g's, find all the a's, transform them into b's using your applicative side effects, and I'll pull the applicative side effects all the way out through the f. And similarly, traverse.traverse.traverse. So I can keep going deeper and deeper. You can actually mix and match these traverse.fmap. They start doing strange things. You have to be careful. And that actually leads us to why we want to do something slightly different. So I want a version of fmap that I can compose with traverse in the same way. So I could say I can go into a functor where I only have a functor for it, but I have a traversable for this other outer container. So if we look at the definition for the class of traversable, traversables have two superclasses. We're going to gloss over one for about 10 minutes until I need it. But every traversable is a function. Because given the definition of traverse, I can choose an appropriate applicative to be able to derive the definition of fmap. Right? I could use the identity monad, or the identity applicative. And then this becomes A to identity of B, F of A to identity of F of B, and I can just put on or off the new type wrapper, and I can derive fmap from traverse. Okay. So that motivates the superclass of functor for traversable. And there is a fmap default that is provided for you in Data.Traversable, which is a valid definition of fmap. So if you've written a traversable instance for a type, you can just say and fmap equals fmap default, and you'll get the functor for it. It'll define it for you. You won't have to like walk through your whole syntax tree a second time doing the same thing just without the applicative side effects. But let's take that guy apart. The source code for fmap default says, I'm going to traverse, I'm going to take the function that you gave me, a function from A to B, I'm going to bolt an identity on the answer. So I'm going to give you an A to identity B. So now that's suitable that I can pass it to traverse. Then this will take in my f of a's. This is going to give me back an identity of f of b's. So I'll run identity to rip the identity off, and now I'll just have an f of b. So this built fmap out of traverse. Just using identity out of like data functor identity. This is in transformers. And these are the operations that you define for applicative. Pure is like return, and this is a weaker thing than bind. So remember we had fmap, fmap, fmap up there. I don't remember how this transition. We can take the definition of fmap default. If we ripped out traverse here, if we didn't make this use the traversable class, if we passed this in as an argument, what traversal I want to use, I could make a function that looks a lot like fmap default. We'll call it over. I have under and some other ones that are related that will come up maybe later in the class. And then if we look at the definition of over traverse of f, this is going to turn into run identity composed with traverse of identity.f. But we know that this is just the definition of fmap default. And fmap default is a valid definition of f. So over traverse is effectively going to do the same amount of work as fmap. And if we give this thing a signature, we're going to be able to go from an A to identity B to an S to identity T to a function from A to B. This is a semantic editor combinator. This is something I don't know. This could be the signature of traversable. What's that? The parens. You can put parens around this chunk. Oh, I missed a paren over here. I did. Yes, I screwed up. This should have a parenthesis here. So we'll call this type here a setter for right now. And a setter lets me just update. I I can't do certain other things to it yet. But a setter can be used to generalize this fmap chain, just like semantic editor combinators did originally. So let's make up something to build a setter. Like we'll make a function named mapped. Because if like fmap wasn't a setter, it was a semantic editor combinator, right? It was the a to b to f of a to f of b, but it didn't have a that identity mucking things up. Mapped basically just bolts the identities in. And then if we look at over mapped of f, this is run identity dot mapped of identity dot f. But we can expand the definition of mapped. So this becomes run identity dot identity dot fmap of run identity dot identity dot f. So we can collapse the run identity dot identities, and we just get fmap of f. So we can see that over mapped is fmap, and over traverse is fmap. Right? So you can pass this thing mapped, or which would work for any functor, or we could pass it traverse, or really anything that I'll call a traversal in a few minutes. So we can just pass this function any like mapped or mapped.mapped, and it will just work. So any setter that I can construct, I can pass to mapped. And traverse can be made to be a setter by just picking the functor, because we're allowed to pick any functor we want, or any applicative we want. We'll just pick the applicative to be identity. Right? The type system will do that for us when we go to pass it into something that expects a setter. Okay? So that gave us the ability to walk into something. So let's maybe use that. So over mapped, add 1 to every element in this list. We go to there. Ignore the laundry list of modules that got imported. But maybe I wanted to say over mapped dot mapped. Right? But notice that this, unlike the lens library that we described at the beginning of this, we can actually change types here. So my lenses can actually go in many structures deep, change out the types, and pull them back up. This is I'm not actually using mapped as a lens. This is a setter still. But setters can still be used to change types. So I said everywhere inside of this thing where I'm going 2 levels deep, mapping through structures, go through and compute the length of each of those strings. All right. I just wanted to actually motivate this with a little bit of example because we've been talking a lot of theory for a little while here. So we can make lots of these things. Like if I had Data.Text. Data.Text is not a traditional, like what you'd think of as like a functor. It's not a container in the classic sense that it's polymorphic in what it can hold. It can only hold characters. But we can make a setter for the characters in a string or in Data.Text. So we can say, if we unpack this thing, now we've got a string. Let's go map over the string and then pack it back up. And this matches our definition for a setter. And then overchars will go in and do the right thing. And then we can go into lists of characters or any traversable container holding onto characters or holding onto text fragments. And we can map over each of the characters inside of my containers full of containers. By the way, how readable is this? So I should have asked that probably a long time ago. This is a lot of small text. I apologize. So derived from the functor laws, I think I can zoom. Control zoom, yay. So if we look at the functor laws, that fmap id equals id, and fmap f.fmap g equals fmap of f.g. In the case of functor, you can actually derive the second law from the first and parametricity. In the case of setters, you can't. You don't get this one for free, given the first one. We can make analogous laws for setters that we would like to have hold. We can say that if you go over a setter with id, it should be the identity. And if you go over it with f and then over it with g, it's the same as over it with the composition. But we can make setters that don't look anything like a valid function. Like here I'm going to walk over both halves of a pair. Right? Here you can give me a pair where the two sides match in type, and I will give you a new pair where the sides match in type, as long as you give me a function from A to B. Okay, and I have to sprinkle the applicative sugar through that. Or I can walk over the first element of this. So given a pair of an A and a C, if you want a B and a C, give me a function from A to B, and I'll give you a function from A to C, or A and a C to a B and C. So this section in fmap. And we can actually see that in use over here. So if I want to go in here and say, sorry for my colorful example. There. So now we're going into a list and then into the pairs inside of that list, where the types of the two halves of the pair have to match originally, and then they'll match in the output. And here I'm passing a function from string to int, and I'm getting out a list of pairs of ints. And we can, of course, do this in a smaller setting as well. Okay. So there's lots of combinators for working with setters. I'm just throwing up here kind of like a scare slide, I admit. The substance of it is that you can construct a setter from a semantic editor combinator or from a functor. You can actually use traverse directly as a setter. We saw that early on. There's lots of combinators for working with them over. There's an infix version of over that is convenient in a lot of code. And then, like, if you're used to just like doing like plus equals and times equals and those kind of things inside of imperative code, if you're working in a state monad and your state is something that you have a lens into, you can do plus equals to modify part of that state. Okay, that will modify all of the targets for the setter inside of your state. So this is actually more powerful than the plus equals notion that you're used to in imperative code, because it can hit multiple targets. This percent equals is actually, if you think about it as mod in to the imperative programmer, right? This is mod equals modify equal. That's why it's modifying it with a function. It was named for a pun. It at least gave you some mnemonic for what the modify thing should be. And we can set or directly just change the value to its new target. This is like passing it const b for this function instead of passing it an arbitrary function. And there's lots of things we can do with setters. Okay, setters I think are a nice entry point to the library because they hint at the structure that we want. We got them directly by looking at the definition of fmap default that was already there, that was already defined for us inside of Data.Traversable. We stole the laws wholesale from functor. We didn't have to make up laws for setters. They were already given to us by the sort of canonical choice of what a setter should look like, which is functor. So let's do traversals. So we saw that we could pass traverse as a setter. What if we tried to generalize this pattern instead of just generalizing the fmap.fmap.fmap.fmap.fmap? Let's do traverse and traverse.traverse. Because remember, over traverse of f gave us fmap of f, right? Gave us your fmap default. So we might be able to define map-m in terms. Map-m is defined in terms of traverse inside of Data.Traversable. But the default definition of map-m, they use this wrap monad and unwrap monad. This is a new type. They're putting it on and taking it off. Here, this guy says, given a monad for m, I'll give you an applicative for wrap monad f. Okay, and since I've got an applicative, I can use traverse. Now that I've gone through traverse, I can pull the unwrap monad off, and I'll have done the work. Using that same pattern of just pulling the traverse out of this definition and replacing it with an argument, we can get a similar definition for map-m that takes the traversal. And so this says, if you give me an S and any monadic function you want from A to M of B, I'll give you an M of T, given a traversal that goes from S to T, given a function from A to B with any monadic side effect or applicative side effect you want. So map-m of can be defined in terms of our traversal, just by pulling traverse out of the function. And so now over traverse gave us fmap, but map-m of traverse gave us unwrap monad.traverse.wrap-monad.f, which is exactly the definition of map-m that's in Data.Traversable. So we can see that we generalized the existing notion of map-m from Data.Traversable. And there are laws that we already know for Data.Traversable. The traversable laws are just these. Traverse pure equals pure, and compose.fmap traverse f dot traverse g equals traverse compose.fmap f dot g. Now, in the end of the slides, I have some references. Jeremy Gibbons wrote a very wonderful paper on the essence of the iterator pattern. In the process of working on this with Russell O'Connor, he was able to prove that these are all of the laws that you need. There were a couple of side conditions that were floating around in the essence of the iterator pattern. Those turned out to all be consequences of those laws. There's a paper he's been putting together that actually goes through with the formal proof of this in Conc, showing that all traversals are planetary containers and whatnot. So this spun off a little bit of research. But the laws for a traversal are just these. Just rip out traverse and replace it with L. Right? So for a valid traversal L of pure should be pure. Right? This is the equivalent to L of return equals return. And in the identity monad, you can see how this the functor law that we started with. And compose.fmap L of f, etc. That one's a little ugly. It's inside of Jeremy Gibbons' paper, if you want more motivation. But really what this guy is saying is that your traversal doesn't change the number of targets for the next traversal. So if you apply a traversal and you would traverse 7 elements, the next traversal, if you were to apply the same traversal, would have to see 7 elements again. That's a good litmus test of whether or not you have a legal traversal. So we've got lots of traversals. Traverse is a traversal. Let's see if I can pan this correctly. Both, which we saw earlier, we wrote both as a setter originally, right? But we were just using an arbitrary applicative. So both can be a traversal. We can traverse the left half of either instead of having to traverse the right. Well, we don't even have the instance of traversable for either, so oops, I think I was supposed to write that. I should do that. But in the meantime, you can use a traversal. Actually, these are called underscore left and underscore right, and they're actually more general than this in the actual lens library. But we can come down here and say over left, add 1 in left of 3. But if I gave that guy right of 3, it would just leave it alone. No, if I gave it right of hello, it wouldn't care about the type not matching. Yeah, but it's only looking for the type on the left. And if we compose these things, it'll walk into the left half of an either, and then into both. Also, notice something here, though. The order of composition here is I'm going into this structure and then into this. The order reads left to right, not right to left. And that'll be really useful in a minute. Because it's the order that like an imperative programmer would kind of expect field accessors to go, you know. I'm accessing foo.bar.baz.quux, adding 10, you know. So if I said, and here is just flipped $sign. It makes for cute syntax. I could have written this thing with, right? An _2 is a very interestingly named operator for basically second as a lens. We have them up to 9. They're actually polymorphic. You can work with them on arbitrarily large tuples. They just do the right thing. Yes? Mm-hmm. We do now. But yes, these are. But it's very hard to correlate those two. It's very hard to program polymorphically over arbitrary size tuples. Yeah, we don't have a k tuple where the kth tuple is indexed by n. You know, for how many? Maybe. Well, we'll have type level naturals at least. So this lets us go through and edit part of a structure. Now, the nice thing about building up in this order is that if I start here, I can start with, say, a blank record. And now this looks like build up a record by setting this field equal to this value and this field equal to that value. Right? You can actually read it off. Okay. And this works for arbitrary setters or traversals or lenses, as we'll see. They all just work. One of the main goals of the lens library has been to make it so that whenever you reach for any combinator and almost any type that you think it could work with, it should do it, and it should do the right thing. And it worked out pleasantly by accident, but it worked out really well. So we've been trying to maintain that property. Okay, so if we go over, traverse left both, we'll be able to walk into a left. All right, so those are traversals. There's a whole host of combinators for working with traversals. In Data.Traversable even, there's a whole bunch of combinators for working with any traversable container. If you take any of the combinators that are in there, bolt of on the end of the name of it, you can pass it a traversal directly, and it will work with any traversal you write. And so that means if I wrote a traversal now for traversing the characters in Data.Text, if you look in the API for Data.Text, it duplicates almost the entire prelude for everything that deals with a list. But most of those combinators are things that you could derive with traversable if it was an actual traversable instance. And so what this lets me do is shrink the API for working with text down to more or less 2 functions. And a bunch of combinators that work with everything. So that, if you're looking for the selling point of this, is that APIs like Data.Text are wonderful. They're really high performance. They work really well. But they don't feel very Haskell-y. You have to import a module. You have to import it qualified because all the names collide with everything else from the prelude. With this, the API for working with text is compatible with the API for working with everything else. You don't have to import anything qualified in order to work with these text fragments. And it really cleans up the code that results. I could actually show that up. Load Data.Text and load a little helper library. I don't actually export this guy by default. And say, if I had hello packed, I'm going to use syntax I haven't introduced yet, I apologize. If I look at that, this is text. I'm saying use something to read out from a lens. So that gave me text. And now I could go through and say, well, if any of the text characters are equal to C in, I'll just say that. I totally can. Well, that made it worse. That's about as good as I can go. Does that work? So any of text equal to C and hello, that was a little too small. I lost myself. Let me shrink this a bit. All right, I can at least put it on the screen now. And any of text equal to C in cello. Right? And this works in both .text. If I had worked with Cello World, we can walk into characters that are inside of a pair of text fragments. Right? And any is a combinator in Data.Foldable, which is I'm jumping all over the place right now. Yes. No. You get a beautiful API and you lose all your fusion. That's the price. Data.Text is very, very performance conscious. And if you really want to maintain that performance consciousness, you probably have to use portions of their API. But if you just wanted to munch some text around and you already have the rest of this stuff open, it can, in practice, be quite useful. All right, so if I zoom back out. So any of it actually doesn't need traversable. It needs foldable. So when I introduced traversable, I glossed over one of its ancestors. And that is that foldable basically provides you with, if you take nothing else away from foldable, it gives you toList as a function. Basically, it says, if you give me an f of A, I can give you a list of A's. Now, it implements it in a kind of funny manner. It says, you give me any monoid, so anything that's where you have an associativity law and you have a unit for it, and a function from A's to that monoid, I'll take an f of A to n. And now, of course, there's a monoid for lists because the empty list and plus plus forms monoid. So we can just use fold map to get out a list of the elements. So if you've never seen fold map before, think of it as toList, and it'll be close enough. So now, when we did traverse.traverse.traverse and fmap.fmap.fmap and dot, we can do the same thing with fold map. So fold map and fold map.foldmap and fold map.foldmap.foldmap, all of these guys work, except instead of this side doesn't keep drilling down, it just keeps going down. So this is, again, the same pattern that we had for traverse. And traversable didn't just give us fmap default, it gave us fold map default. It gave us a version of fold map for free. If you know how to traverse something, I can give you fold map for that thing by default. And here's where we need the generality that traversable gives us. So traversable doesn't need a monad. It needs an applicative, or it can work with an applicative. And I'm going to work with something that I can't make a monad for. Const. And const is provided by control.applicative. And it basically says, if you give me an, const ma doesn't have any a's in it. Right? It's just m's. This is a functor really easily. I don't care about the a argument. I can just throw it away. And I can rip the const constructor off and I can put it back on with a completely different type. Right? The only thing that I kept my m, and that was the only thing that was in my const constructor. And I can make an instance of applicative for this just by saying, well, when I go to make up a pure value, so like return, I have to go from A to M of A, where I have to go to A to const MA. So I need to come up with an M out of nowhere. So I can use M empty from my monoid, right? So this is saying I can construct a value. I don't care what value you gave me because I don't have any place to put the A. I'm just going to throw it away. And if you have two const values and you go to app them together, that's how we read that symbol. I'm just going to use append, the little alias for it inside of Data.monoid these days. So I'm going to use the binary operation that we got from our monoid to stitch together my monoidal values. So given a monoid for M, const of M is applicative. It's a functor regardless, and this will be important later, so I wanted to make that distinction, right? So const M is always a functor, and if you have a monoid for M, it becomes an applicative. We need the monoid because we don't have any other way to magic up a value for it when we don't use it, or when out of nothing, and we don't have a way to stitch them together otherwise. And the associativity of our monoid is enough to give us the associativity law that we need for applicatives. Okay, so now we can look up at fold map default, and fold map default, kind of like how we used run identity over here, to just say we're going to give you an A to an identity we're going to give you an A to identity B by just wrapping this in identity. We're going to do the same thing by wrapping it in const. And we're going to get const on the other side. So this is just the accessor for const. So this is basically saying that I really don't care what choice of B you make. Because the F, or here, I don't care what the choice of B you make, because I'm just going to rip const MB down to M in the end anyways. So fold map default is defined in terms of traverse. We've kind of established a pattern for what we do for functions that look like that, though. So, and here I go stupidly dense again. Let's see here. So taking fold map default, we can take it apart. We can pull traverse out of it, replace it with something we'll call L. We'll just pass it in as an argument. We'll type :T inside of GHCI. We'll ask for what the type signature is, and it will give us a signature that works. Right? I didn't have to make anything up. GHC told me what it should be. And then we can make up, kind of like when we did, when we worked with setters, we built mapped so that overmapped turned into fmap. I want something so that I can pass it so that when fold map of is applied to, say, folded, this should be the inverse. This should give us a fold map of that. We want to do the same thing. We just want to do it for a different class. We want to characterize a fold. So fold map of was get const.l of const.f. If I choose folded to be const.foldmap of get const.f, then fold map of folded turns into get const of const, a fold map of get const.const.f. And we can destroy these to get const.const. And this becomes fold map. Right, so we've gone through the derivation. We've proven that this is, sort of the fold, as it were. And given any fold, we can define this combinator we'll call view. And view says, I'm just going to pass const to your fold, and you can now get const. Okay? So, going back to abusing things I haven't introduced yet, if I view 1 out of hello world, I get hello. Okay? Maybe that's not a good example. If we use view folded, we'll say, if you give me any foldable f and any monoid b, and I'm going to give you another horrible type signature. I'll give you a function from f of b to b. Right? We can just ignore the reader. This is generalized, so you can use it in Mono Transformer stacks. The actual documentation for this is really nice, and it gives you about 10 fake type signatures that you can look at view as having to think about it. But when we view folded, they're inside of Data.Foldable. Instead of foldable, there's fold map, there's fold R, there's lots of generalizations of the common folds that you work with for lists. And one of them is called fold, and that's just basically saying if you have a container full of monoidal values, I'm going to let you like calculate a monoidal sum, basically, of them. Like you just stitch them together with whatever the action is for your monoid, right? So we go to view folded. This is going to turn into get const fold map get const. This is fold map of id, which is the definition for fold. And we can make up this guy. We'll call it, fold is going to say that for any choice of m, you pick any. Oop, this is missing a monoid constraint. For all m, such that there's a monoid for m. Give me an a to const m of a, I'll give you an s to const m of s. So that's a nice way to work with lots of containers. So we can work with anything that we could do with Data.Foldable, we can do with a fold. So like any of, some, product. There's a whole like 50 combinators or something in that library. They all generalize. So sum of both will go through and add up both elements out of a pair. Or sum of traverse.both will go through some traversable container full of pairs and add up the values of all of both sides of the pairs inside of those traversable containers. So what if we wanted something that was more powerful than a traversal? So we look at this signature here. Traversal, setter, fold. We wrote the definition of view, and I've got a whole pile of stuff on this slide. I'm sorry. We wrote the definition of fold map of. ToList of says basically if you give me a, I can convert it that way. I got _1, which would walk over the first half of a pair. I don't need all of the power that traversal gives me. Traversal says that you pick any applicative, and I have to be able to plumb those effects through. Here, I'm only using the functor. Here, I don't care about your monoid. You know what I mean? I was saying that view took a fold before. But view doesn't care about a monoid. Your L, your particular fold, might care about the monoid. So if I just wrote this code without any signatures on it, and I said view _1 out of 10, out of a pair of 10 and 20, it'll just give me back 10. Without a monoid on integers. That will work. So I obviously missed something. So if we add a couple of additional members to this hierarchy, we can fill in the gap so that we can make the signatures for view and the signature of ToList of, and all those things make sense. So what we want here is a lens, or let's just say a getting, would be I'm going to get out something. I'm going to use this particular monoid or this particular constant inside of my const constructor. It may not be a monoid because I'm not saying that it works for any monoid. I'm just saying it works for R. And I'm going to say a to const r, s to const r. So I've lost some power from fold, but I've gained the ability to work with this in particular. And if we just wrote the signature of view would look like getting a out of STAB. So remember STAB was saying that given a function from a to b, I can take it from s to t when we were talking about setters. Now t and b are completely irrelevant. We don't care about them. We're just going to use them so that we can actually pass the same lens into a getter and to a setter. And I'm going to just pass this guy const. So this is now going to be a to const ab. And now this has to be s to const at. And so I get const out of that, and I just get the a that I packed in here. So this gives me the a out. And so view didn't demand a monoid out of the elements of my container. If you happen to use it with a fold, we'll demand a monoid. Because this says this works as long as you can pick a monoid for m. But view itself doesn't demand a monoid. Fold map of even doesn't demand a monoid. Right? All I'm doing is I'm applying your function going from a to some value type, we'll call it m, for convenience, but I'm then wrapping it in const. So all I did was the same thing as view, I just bolted a function in, and I'm getting the constant value out. So I'm getting an m out. It may or may not be a monoid. So when I apply fold map of to a fold, I'm going to demand a monoid on m. But if I apply it to a getter, which I haven't introduced, I will not. So what we get is we have setters, we have getters. I am missing getter in that list, aren't I? So what we can do is we can make this notion of a lens be any traversal that is a valid getter. And I am missing the punchline because I am missing getter on this slide. But we can write the definition of getter. So type getter, STAB, getter SA, equals for all results, given an a to a const rb, I can give you an s to a const r. Take a, because I didn't give those names. So we can define this by analogy to the fold, where fold said you can rely on the fact that I have a monoid on R. And a getter doesn't give you this. So you have to, this has to work for any function from a to const r, a, which is just, this is effectively a function from, give me a function from a to r, I have to give you a function from s to r. And I can know nothing about r. And since I can't know anything about r, I can't put it together in any meaningful way. So all I have to do is find the one r inside of your structure that this is referencing. This is a fancy way to say that I have a function from s to a. Do I have getters? All right, I'm going to skip around in my slides, sorry. So a getter is, you give me a function from s to a, I will give you a getter. Which is that for all r, a to const r, s to const r. And we can build two. And this guy says, if you give me a function from s to a, and a function from a to r, with some new type noise, right? I can give you a function from s to r, with some new type noise. Well, that's like flip dot. And some new types. So we can say 2 is compose these two functions and then rip the const off and put a const back on. Okay? It's kind of boring. And then when if we view 2f, this is going to be just like we did before. We'll plug in the definition of 2. We'll get const.const.getConst.const.f. let them cancel, you get it, right? So we can lift functions now. So now we can drop functions into our little lens-like pipeline and get something that's kind of like a lens, kind of like a traversal, kind of like a fold, but it's just a function that gets one value. And Vue didn't demand it be a monoid, it just works. So now we can go back and look at the lens, sorry. So now, a lens, then, is just a traversal that is a valid getter. So it's a traversal of one target inside of the structure. And it has to traverse one target because it has no way to build this f to give it back to you other than to use your function from a to f of b. Right? I have no other knowledge of f other than the fact that it's a functor. The only thing I can do with a functor is fmap over it. And the laws on functor are such that really it doesn't matter how I fmap over it. If I fmap and then fmap a second time, I could always smash that together. So what this means is I have to go into my S, find an A somewhere. I have to concoct one up, by hook or by crook. Find an A, give it to you by calling your function, get an f of b out of it, and then bolt the rest of the crap that was inside of S onto the answer inside of the functor. There's nothing else I can do. So a lens now, under this formulation, is just any traversal that happens to be a valid getter. Because a getter just said that this went to const r, and we knew nothing about this. But we knew that const r was a functor no matter what choice of r we picked. It's not applicative unless we have a monoid. But we only needed the functoriality of it in order to be able to work with lens. And I went really fast through that, so there will be hopefully a video to go through that derivation again. But what we can do with this now is we had view and set. Set let us write to a lens, and view let us read from a lens. If you remember way back at the beginning when I started with that data lens thing and then promptly threw it out, we can now derive the definitions from that slide in terms of this much crazier looking construction, right? Here, view is picking the functor to be const for const A, and set is picking it to be identity. We're just choosing two different functors out of the, we're allowed to pick any functor we want, so I'm choosing them to be identity or not. And so using that power, we can read the single target out, or we can set it. But interestingly, if I pass this guy a fold, now, spontaneously, this is going to start demanding that this argument be a monoid. And if you don't have a monoid for it, then you can't view the answer of a fold, because it doesn't have any way to smash together all of the different answers for you. So view works for folds, it works for lenses, it works for traversals, because every traversal is a valid fold. So it will just view all the targets of the traversal. And what we get is sort of a subtyping relationship between all of these different type aliases, right? Where using them in different contexts cause these combinators to demand different things of you. So when we did view earlier, when we viewed _1 out of hello world, _1 was a lens. A lens is a valid getter. A getter reads exactly one target and doesn't demand a monoid of us when we go to view from it. But if I want to view both halves of this, it would have to do something, because it's got to mash them together and give you one string, but it has two strings. So it's going to use the monoid for string. And if we really want it, we can get them out separately, because we can just convert it to a list. Huh? Well, if they're integers, it's going to complain that it doesn't know how to do this. You both. It doesn't have a. But we can say, give me the sum of both. Because that's going to pick a monoid. That's going to inject them into the sum monoid and then do the work there. Sure. Mm-hmm. Yes. Yes, and that is the instance of monoid for string. Yes. So yeah, so by default, you could make up an instance of monoid for integer. Yes, because do you really want to add them? Do you want to multiply them? There's lots of things you could do. So when there's no one right default, we just don't pick one usually, and then you have to pick it with a new type. Well, you can use a new type wrapper around it. Like I could use view both of. I'm going to just stick these in the sum new type. In the sum new type, so, and then we could get sum to peel that off. Okay, so now we were able to build with view and set. We can construct a lens given a getter and a setter, but now we've got these funny B and T type parameters floating around here. So we should probably speak about why that changed, right? Because remember we were allowed to change the type of our targets, right? So before, when we talked about lenses, at the very beginning, we just said that, well, if I start with an S, I can get an A out, and if I've got an S and a new A, I can put it back in and get a new S. Here what I'm saying is, maybe you want to change the type of that target, or all of the targets. Well, one target, because we're in a lens. If you change the type of that target to a B, the new type has to be T. Okay, and it turns out that you get this family structure where you've got like the outer family and an inner family, and they both have indexes, and I've written a blog post on the topic if anybody wants to drill in deeper. But the structure here usually is a good way to tell if you've got a valid lens is if you could always pick S equals T and A equals B, and it works. If you can't, then you probably screwed up and you don't have a lens. Well, you definitely screwed up and you don't have a lens. It's a good litmus test. So if I know how to go from S to A, and a B and an S to a T, and an A to an F full of Bs, and I have an S, I can take my S, feed it to my S to A. Now I've got an A. I can feed it to my function from A to an F of Bs. Now I've got an F full of Bs, so I have to fmap over that to get to the Bs. I can get the B that was in my container and the S that I started with and smash it together, get a T. So now I have an F full of Ts, and I meet that signature right there. All right. There's documentation. So again, a lens updates a single target, and you can define a lens in terms of a getter and setter pair. In practice, I never bothered to do it this way, because it's easier for me in practice to just say underscore 2 of F and a pair of A and B should look like, I'll just write it, I'll say my underscore 2 so I don't fly. That's a lens. As soon as I have everything I need. Okay. Also notice something here. I didn't have to import my library to write that. Right? So you can write lenses that are compatible with the lens library. You can define traversals that are compatible with the lens library without depending on the lens library. Right? I just used this. I could have used fmap out of the prelude, and I wouldn't have had to import anything. Okay, so using just the prelude, you can define a lens that is perfectly compatible with all of the combinators I give you inside of the lens library. And one of the reasons that this is important is that if you view Cabal kind of like an onion or something, where like packages come along and they just get they're layers on the onion, right? Later packages kind of have to provide all of the stuff for packages that are deeper than them in the list. It's really hard to invert a dependency in the Cabal world. And you can't have cycles. So if I were to come along later and define a library that I could have some great instances for containers. I better put them all in my library because there's no way I'm getting containers to depend on me. On the other hand, with this, I could try and convince Johan or somebody on the containers team to make a lens to go traverse a given element out of a map. And that might be an argument I could win. And so somebody made a joke that I've gotten to the point where I've optimized my libraries to the point where you don't have to depend on them anymore in order to be able to use them. I think this is a really big selling point for this kind of lens. If nothing else, because it solves that, well, which lens library do I provide the lens for? You don't have to pick up a dependency, you just write a function. So this is, I think, pretty cool. And then the other thing is this just magically becomes a traversal if I started to say, well, and block this one too. Done. Okay, so traversals and lenses can both be provided by any library without even depending on me. Okay. Did I miss an A somewhere? Oh yeah, I screwed up an A. Woo-hoo. If you can write code correctly. Yay. So given a pair of t's and a function from t to f of a, I can give you an f of a pair of a's. But now, because I have to be able to smash together the answers, I need the applicative. And that's the thing that will magically make it depend on a monoid when you go to use one of the fold combinators on this. So you can use this traversal as a fold, as a traversal. It just works. You can use this lens, the my_2, as a fold, a getter, a traversal. All of those things they just happen to be instantiations of the type that we get. All right. So we can now make, I'm missing the definition of that. So if we want to go define a lens into a map, like naively we might say, well, given a key into the map, I want to go get you the value at that key and be able to write to it. That doesn't quite work. Because what if the value is missing? What value do I give you as the input to your setter, right? So I can't do this. When I go to write this, I get stuck. I might be able to make a traversal that will traverse the element of it and let you update it if it's already present. But that's not letting you create a key out of whole cloth. But what I can do so we can say map.fromList. This is going to build a map for. So this is a map you can insert and delete into it. It builds a nice size balanced binary tree. Performs really well. So we can read it at hello. This is an infix form of view. We can read it at a key that's not present. And notice that this is a lens that's getting out a maybe. So let's delete from it. So I can read and write to it, but I can not only read and write values, I can delete keys from the map using the lens. And that's how I can meet the lens laws. Is that not only do I read and write, I can delete. Because I can go from, given a key, I can give you a lens that looks at the value of that key if it's present, or gives you nothing if it's not. And it will insert it when you go to update it, setting it to just something. And it will delete it if you go to update it, setting it to nothing. Now, @ is actually generalized so that it works with int maps and hash maps and whatnot. But Conceptually, you can think of at as having this signature with a maybe a on the end. All right. So folds are like foldables. We talked about folds. There's a whole bunch of combinators you can already do for foldable and data.foldable. Like, there's a lot of them. We duplicate them all with this of convention. I think Lens provides something like 600 or 700 different names for things that I actually did a word search, like frequency analysis against package before releasing the library to try and minimize their conflicts. So that's why we do the of convention and stuff like that. We use lots of past tenses. I take names in places that nobody does, like we use gerundives and so gerund, so we use foo-ing instead of, so that's why it's folding and folded and stuff like that. Past tenses. So things that get us names that are declarative but are relatively underutilized portions of the namespace so that people can import Lens unqualified, because control.lens brings in all of this stuff. And I really didn't want people to have to import something qualified or explicitly name everything that they use. So, because it's really hard to give a talk if you have to name every word that you're going to use in your talk before you can use it. Right? It's much nicer to have a large vocabulary that you can just reach for. And in many ways, the Lens library is all about building that vocabulary for working with functors and foldables and traversables and functions that we already know how to use, right? So all I did was take the pieces that we already know, that we already know how to reason about, those four things, and put them together in a form that makes them more composable and makes them more applicable, so that I can just say, just grab this combinator off the shelf that I could use on this limited portion of them, and now I can apply it to the entire gamut of all of those possibilities. Okay, and so there's a couple of these that are really convenient. If you have a fold or a traversal that is probably 0 or 1 elements, you have something like maybe it'll give me an answer, maybe it won't. This guy will go get you the first answer that we give. So caret question mark is used a lot. Caret dot dot gets you a list of all the answers. So like I've been using caret dot, which is it's view flipped in fixed form. A lot. So the tilde on the end is for like setting operations. It's like it's functional setters. It's apply this operator setting, and caret dot is caret something is usually I'm reading from a container of some sort. So here I'm reading from a fold and giving you maybe an answer. Here I'm reading from a fold and giving you all of the answers. The dot dot should be indicative of the dot dot syntax inside of So we can go through and say, given 1, 2, give me both. And I've lost my ability to type. Awesome. All right. Apparently. So 1, 2, 3, 4. Traverse and give me both. Okay. Or both, not both. All right. And then let's say that we had, I don't know, left 3. Tell me whether or not that is left. And so most of the things that you can do with data.foldable, you can do directly. Well, actually, all of the things that you can do to a foldable container, you can do, and most of the things that build up a structure actually get. Most of the things that you can use to build up a list can actually be used to derive a fold. All right, so I skipped around my slides a bit. I did getters out of order. So getters are just like functions. And this is actually where I was supposed to introduce. I get a little behind myself. I actually implement these in a little bit different way. Like up until now, I've been saying that that you just pick identity or you pick const. I actually use a class for it because if I actually just picked const or identity and I went to go read from a setter or write to a getter, I would get a terrible looking unification error that would be like a screen long. Okay? But if instead I put a class constraint on it, it will unify, and then it will go look for an instance that isn't there. And that will just say, no instance for settable accessor, or no instance of gettable mutator. And that looks much nicer, and someone can intuit what they did wrong. Right? So I actually implement that const construction by making a class for things that are gettable. I can just say I can coerce f of a to f of b, and the law is that fmap of f, or fmap f, equals coerce. So this can't have an a in it, because in order to satisfy that law, I can't use the function to map over it. And so once I get done with that, now getters look like the way that we built traversable and functor, or traversable and lens, right? Or traversal and lens used functor and applicative here. Here I'm using gettable. And then, so instead of taking on and pulling off and putting back on a new const wrapper, I'm just saying coerce. Turn an f of a into an f of b because I know that thing's irrelevant. And getting can still pick it to be accessor, which is just a fancy name that I gave to const, so that when you go to the setter, it goes to look for settable. And then settable for accessor. So, with that, we've got lenses as just anything that is both a getter and a traversal. We got a whole pile of combinators for these. So in addition to updating the target, I can read the answer that I wrote at the same time, because it's awfully inconvenient to go, oh, I updated my fresh variable count, and then have to go read it again. So like with this, you can go through and define something like, I don't know, let fresh equals no monomorphism restriction. There. So this will say, in any monadic state that has that has a numeric type, I can bump the counter by 1 and read the new value, all in one pass. Okay? And I used the identity lens here, which, by the way, is just the identity function. So I've been composing these things all along, but I haven't really talked about why they compose, right? Well, if we look at this, this is a function from a to f of b to s to f of t. And when I compose them, I'm composing those functions, the outer wrappers. So I'm going from a to f of b to f to f of t. And I have something from here that goes from, I don't know, x to f of y to a to f of b. And so when I compose those, now I go from x to f of y to s to f of t. So I'm just composing these larger blocks. That's why I can use dot from the prelude. You can actually build these things using arrow sugar if you really want to, even though they're not arrows. Just pass the ones. Everything composes backwards because if you look at this as kind of CPS. So we've got lots of things we can do to lenses. Our getter built us just a CPS function and put some new types on it to build it. Now let's do something fun. So up until now, we've been just kind of manipulating f here. There's a hack that I came up with, I don't know, about 4 years ago that I used in a little toy library for like overloading function application in Haskell. Everybody says you can't do this. Not everybody, but a lot of people say you can't do this. But you can. Right? You're not allowed to make a data type where you define how it applies to values. But what we can do is we can make a class such that our data type is an instance of the class and a function is an instance of the class. And then we can get overloaded function application. And what I want this for is I just want to be able to define a function which I can run backwards. Okay? And then I want to turn it into a lens. But let's just do this like in small steps. And this slide here is a bit of a lie. This isn't how we actually do it in Lens anymore. This is the way we did it up until 3.6. With 3.7, it's changed. But I think this is a better exposition than the current approach. But this trick would work in the wild. You could do this for anything you want to do. So let's say you wanted to make isomorphisms, such that an isomorphism was a function that you could apply like any other function in Haskell. But you could also use from to turn it around to get an isomorphism in the other direction. So you could apply it, but then from would be id. So what we're going to do is we're going to say, I'm going to make this class, and for want of a better name, I called it isomorphic. It's something that I can construct from an isomorphism in Haskell. So if I have a function from A to B and a function from B to A, such that this is the inverse, they're mutual inverses, I can give you a k from A to B for some k. And now I could make functions themselves be an instance of isomorphic just by ignoring this thing. I can construct a function from A to B, given a function from A to B and something else. That's pretty boring. And then I could make this data type isomorphism, which actually captured both. And this would also be a perfectly valid instance of isomorphic. We'll just make isomorphic equal to the constructor, and we'll capture the A to B, and we'll capture the B to A. Right? I used both sides of it this time, instead of throwing this one away. And we can make a category for isomorphism, so that we can compose isomorphisms. So you'd have to import control that category to get its version of dot and id in order to be able to compose these. If you didn't, they're just going to dumb down to functions when you compose them, which is actually perfectly good for us. So now we can say, id is an isomorphism using the two identity functions. If we had a function from B to C and C to B, and one from A to B and B to A, we can smash them together the only way they fit. We make an instance of isomorphic for isomorphism. And then we can say that a function from A to and from B is anything that is isomorphic of K from KAB. So this can choose this K to be a function arrow if you use it in a context where it has to be a function. And it can choose K to be isomorphism if you use it in a context like from, where it has to be an isomorphism. So if I need access to both sides of a function, I can turn this guy around and give you a new isomorphism. So now with this, I could say, isomorphic plus 1 and subtract 1. And I could name that function f. And I could apply f to 5, and it would give me 6. But I could say from f 6, and it would give me 5. And the composition works. So this gives us overloaded isomorphisms that work as functions, but I want them as lenses, right? One of the ways that we build lenses in a lot of other lens libraries is that we use like a function named iso and just give the isomorphism. And then we kind of forget the fact that we can construct it out of whole cloth the other way. We use this as the setter, and we just ignore the A that we're passed. But I want to have that full power to turn a lens around if it is based on an isomorphism. I want to be able to run it backwards. So like I did inc here with the plus 1 and subtract 1 example. So let's make iso kind of like lens and traversal. What we're going to do is we're going to pick k here, the outer function, the function that we're between a to f of b and s to f of t, to be k, where k is an instance of isomorphic. And so now I can give you a function from a to f of b to s to f of t, or I can give you s to f of t to a to f of b. I can pivot around that central arrow. Okay, this is the old way. The signatures change a little bit now. But this at least gets you an intuition. And so this used to require us to provide us all 4 functions. The new version actually lets ISO be both of these, and you only have to apply 2 functions even when you want to turn them around. But all we're going to do is say, you give me the two sets of mutually inverse functions, and I can give you an isomorphism family that works kind of like a lens family. And then we can go through and say, we can make an isomorphism between string and text. So that text, or so that packed, this will take string to text by packing it using the pack function out of Data.Text. And we'll take text to string by unpacking it. We'll call it an isomorphism, ignoring illegal characters and stuff like that will cause it to flip out. And then we can define our text traversal that we used earlier on as just from packed. So take this isomorphism lens and run it backwards. And then traverse the contents. So now I composed an ISO with a traversal, and I got a traversal. Because what happened was, when I went to do this composition, this forced the outside to be an actual function arrow. So this picked k to be function arrow, which is a valid instance of isomorphic. Here we turned packed around, so we used it as an isomorphism. We got a k be a. We chose k to be a function arrow, and we traversed. And so this is where the cello world example actually was supposed to come in. All right. In practice, we use a more horrible encoding for ISO that lets us be a little more minimalist. And there's actually a similar construction for these things we call prisms. I'm not going to have time to go into prisms today, but prisms are what happens if you take the categorical dual of a lens. So a lens lets you access one field of a product-like thing, or part of a product, and a prism lets you access one constructor out of a sum. And so left and right are actually prisms. They're not traversals of the left and right-hand side. So that's the bulk of the talk. I just want to show a deep dive on a couple of quick things, and then I think I'm done. How am I doing on time? Okay, that's about perfect. So how many of you have used Uniplate or heard of Uniplate? Okay. So Uniplate is a library for doing generic programming in Haskell. It's written by Neil Mitchell. It's really nice. It performs really well. It's fast. I embedded a copy of Uniplate inside of Lens, which seems kind of redundant. But what I did was I redefined the Uniplate combinators so that they are valid traversals, or rather, so that the combinators can take any traversal, and that Uniplate and biplate are actually traversals. This actually solves a number of problems with Uniplate, and then has the side effect of making it 35% faster. So what we can do is we can define a class. We'll just say plated is a class that knows is a traversal that knows how to get A's out of an A. It's like, go find all of the subtrees of my children. If you have a syntax tree, go find me all of the child nodes, one level down. Give me the immediate descendants inside your syntax tree of the same type. Go find a sub-expression of your expression. And say by default it is ignored, or it uses one of these guys that uses data.data to build a complex hit map using all the logics that I stole wholesale from Neil's library, which was awesome. But in Neil's library, he goes through and he builds up a data structure to kind of mimic the shape of the intermediate structure. And I don't have to, I just captured it in the environment. And so since I'm not building up and tearing something down, I save all that time, and that's where all the speed up comes from. But you can make explicit instances of plated. And then unlike his combinators are rewrite, which would take instance of Uniplate, which is his class name for plated. We just have rewrite of, which is parameterized on, in this case, a setter. Most of them take a traversal. Ignore the scary looking signatures because I literally cut and pasted them out of the code. But these combinators are actually really nice in that I can do some pretty hideous things, like using these for generic programming. We can use byplate to say, go look for hello world. There are strings in here, and go find them all. Helps to bring it in. Data lens. I should probably pick this to be, and go find me all the strings rather than all the units. And so that went into the tuple. It used generic programming to find all the strings anywhere inside of that data structure, as long as the data structure it was an instance of data, and the thing that I was looking for was typable. But I can also update them because it's a traversal. So take that thing and tell byplate to modify everything, convert it all to uppercase. It helps me to have why don't I map m of underscore, which we'll go through and run an action on byplate, and put stir line. Right? We can do all these things. All of our generic programming traversals just work. And we're able to use byplate as kind of a magic traversal that will just be whatever traversal we kind of want it to be. So if you're too lazy to write the traversal, it's there. So that's Uniplate in lens form. It comes with a lot of combinators that were in the original Uniplate that are really, really handy for rewriting syntax trees and whatnot. Like rewrite of, we'll say, give me a setter that knows how to get A's out of A's, and give me a function from like A to maybe A that like is a rewrite rule you might want to apply. Maybe it goes through and looks for negated literals and turns them into the literal that is the negated value inside your syntax tree. So if you have neg of lit of A, it'll turn it into lit of the negative value of it, right? And what it'll do is it'll apply this in a bottom-up manner. It'll go into the A's, the descendants of A, of your top-level expression, look for the sub-expressions, look in the sub-expressions of that, keep going down, apply the syntax, the rewrite rule at the leaves until it doesn't apply anymore, and then walk its way up the tree. That's one combinator, and it works for doing hierarchical rewrites. Context of holes of will find all of the one-hole contexts as a context comonad. So that's the store comonad from the beginning of the talk. All of these combinators were derived from plated. They all work directly on any traversal. It's an incredibly powerful addition to the library. And then there's one other kind of like deep dive example I want to do, and I'll probably go like 5 minutes. And that is zippers. So one of the questions that I get asked a lot are, what is the connection between zippers and lenses? And historically, there really hasn't been one, but now there is. So Zipper provides a pretty nice API. So what we can do is we can say, I want a zipper into something. Let's start with Hello World. I like Hello World. So what is the type of this? So this is a zipper. And the way that I'm going to view these things is they look like breadcrumb trails. Okay? So we're starting at the top. And we're looking at two strings. And go down and, change the name. We were conflicting with too many people. And so now, unfortunately, GHC decided to put unneeded parentheses around this. But if you read this like a breadcrumb trail, like on a website, this is saying we're starting at the top into a pair of strings, and we're down in one. We're down looking at strings. And now we're looking at a single character. And I want you to change the focused element to J. And I want you to move all the way to the right and change the focused element to Y. And rezip. I'm looking at the types. I should probably actually show you the answers, huh? So we walked down into the first half of the pair. We walked down into the list here. From within, like, basically makes us a level where we can move leftward and rightward within the level. So we pick a traversal, and we can move left and right within the traversal. So like left and right inside of a zipper are traditionally something where you have to make up a notion of left and right that makes sense for your syntax tree or whatever. And you had to figure out a class or something for how zippable worked or something like that. Now, you give me a traversal. Zipper doesn't have any constraints on A. I can walk into anything. Give me a zipper into 1. What's the type of that? Is it, 1 as an int. And give me, let me have some combinators for working with this. If it's lens and traverse, or end from within the bits of that, and set the focus equal to false. I'll just, in the end, I want to rezip it. So I went into the individual bits of an integer, starting at the, the least significant bit. I can move left and right through the bits, setting them, pop back out of it, and it just uses the fact that I can traverse individual bits inside of a numeric type. Okay. Any data type that you want, as long as you can build some kind of lens or traversal into it, you can use the zippers that come with lens into. And then up and down, pop the breadcrumb trail, pop or push onto the breadcrumb trail. So given a lens, it'll go down. Given a traversal, that could fail, because there might not be a first element for the traversal to go into, right? So within has to give you kind of maybe you succeeded in going down. Left and right actually became leftward and rightward. These guys, lefts and rights are dead now. We have combinators for tug and jerk, which let you tug or jerk the zipper left or right. If you tug in a direction, it will go and gently stop at the end. If you jerk it, it will fail. So if you try and go, if you tug left and you're already at the leftmost element, it will stay where you are. If you jerk left, it'll just give you nothing. It's okay, a little cutesy. But but the names were not taken, I checked. Nobody wanted to use those names for some reason. One little physics library had jerk as like a third derivative. So that's basically what I've got for zippers. There actually happens to be a lot more in the library. We've got so if you're interested in more, there's the Haskell Lens channel on Freenode. There's about 45 of us lurking in the channel at all times, answering lens questions and working on the library. There's a lot of build.bat spam because there's I think we have 7 or 8 committers in the library now. It's making fairly alarming progress. We're on version 3.7. I started it 4 months ago. Sorry for the ever-breaking API, but it's a better library for it. So the community is pretty good. There's a number of resources out there for learning more about lenses. So first of all, there is the lens.github.com will give you a very not fitting on my screen website that gives you more about them in a tutorial and stuff like that. And so there's a longer tutorial on how to use lenses. There's the actual GitHub website for Lens. Feel free to fork the library if you find something wrong with the headex or whatever. There's about 500 example doc tests that actually get run every time we check in that keep us honest about the documentation. There's a wiki that has lots of the stuff that I worked through on the derivation, a fact about why we did things certain ways, etc. There's a lot of resources out there. I tried to keep as much of it as community editable and updatable as possible because I'm only one person, and for some reason a lot of people want to use these. And I want people to understand lenses. So I hope this has been useful. That's all I've got. Oh, if I have time for questions. Sure. Sure. I'm trying to be political. My problem with the Scala Collections library is, for instance, if you look at like map in Scala Collections, Data.Map, their map data type, traverses pairs of key values where you can't really reason about like the functoriality of map. So if you want to work with map, you have to map over map and then convert it to map, literally. So in order to work with map, you're almost always working like with 3 functions that have map in the name. And so, to me, one of the strongest things that I get out of Haskell is parametricity and laws. When I look at the Scala Collections library, there's very little that you can use out of it parametrically. There's very little that you can go, oh, this holds across all containers. I can just use this combinator. I have to use ad hoc thinking on a per collection basis. For instance, here we have index traversals for maps. So there's a whole, I didn't talk about index things at all. But like if you want to have access to the keys inside of your map while you walk over it, I have something very similar to that isomorphism hack that lets us work with index traversals as well. So that you can have access to the keys inside of your map as you traverse the list of all the things. And you can get an index list of the contents and stuff. I find that particular approach to be much more practically reasonable than the Scala Collections approach, where now I can map over the contents, but I can't reason about that map f.map g equals map f.g, because I might map, and in the meantime I might smash 2 tuples together that now make my map, I now have fewer elements in the subsequent traversal. I like laws. I like the ability to understand my code. In my experience writing a lot of Scala code, I have not had that.
I guess what I was getting at is when you say, oh, here's a lens library, you don't think of it as a generalized collections library, but it sounds like that.
You know, I really should have named the library Traversals or something, but then nobody would have looked at it. It really is all about all of the things that I happen to be able to use the lens combinators with, and not lenses in themselves. Because everybody hears the word lens and goes, oh, I know what that is. I've looked at FC labels and data accessor and data lens. And really, I think after going through that talk, you got a feeling that this is not about that. It's basically everything that I can take out of the handful of classes that we already know how to use in Haskell and generalize them so they compose better. Is that all right? Yes. The type synonyms, yes. Actually, you know what? I can do it better. I have a UML diagram. We are so object-oriented that even our accessors have accessors, or have. Yes. So I have an actual UML diagram describing the relationship between those different classes, right? So we can say that every traversal is a valid fold, right? Every traversal is a valid setter. Every getter, we actually have these things called actions and monadic folds I didn't get a chance to talk about. We can come down the diagram and see that every lens can be used directly as a getter. Every lens can be used as a traversal, and therefore can be used as a fold and as a monadic fold, right? So every isomorphism is a valid lens and a valid prism, which is the thing that I didn't get a chance to talk about. And both of these are valid traversals. Oh, sure. Let me go back to the slides. I wanted to sneak that in there. So there we go. I think that works. Yes. As soon as I drop pure and app, I get lens. Yes. Yep. So if you weaken functor so that the functor doesn't use the argument, you get gettable, which is that class I introduced briefly, right? And then you get a getter. So if you have just the gettable instance for app, then you have the actual getter class that we use. And then if you have gettable and applicative, you have the ability to smash values together with pure and app, but you know that the actual values that you used for pure don't matter. And so you get a fold. So gettable, applicative, functor, that hierarchy is how you can derive everything except for setter. Yes, in this case, in practice, I have a settable class that says it's isomorphic to an identity. It has no content other than the value. And I actually abuse those classes to make, there's a number of combinators I didn't get to show here, like there's backwards and forwards that will like reverse a traversal or a len or a setter or a getter or a full, they'll turn like the list of all of the things that it's going to visit, so it visits them in the opposite order, even for all those restricted types. And those actually wind up being kind of like applicative transformers that I apply to the applicatives that I build up. So I actually abused that class thing that I introduced so that I could get better type errors to make a lot of very generic combinators I wasn't able to get to. Yeah, it's really just how we instantiate F, what constraints we put on F that choose how these things interoperate. And that's how we get, I guess, the sort of ad hoc overloading that makes lens go. Yeah, this is basically whether or not it's allowed to be any monoid or any value, or if it has to be a particular value. So, and then, like I said, these are actually all implemented by classes except for getting, which is. All right. Anybody else? Is there a hand up? Oh, shit. All right, I'll let you go first, and then I'll. What's up? Oh, there is a notion of strength of every functor is strong in Haskell that we abuse very. The implementation of lens in here abuses the strength of every functor in Haskell. So one way to construct a prism is to abuse co-strength of certain functors that allow you to go search for sums. We can lift like an A and an F of B to an F of A and B. Every functor in Haskell is strong because of the way the environment works. Not every functor in Haskell is co-strong. I have a blog post on strength versus co-strength. I think it's deriving strength from laziness or something like that. Look on combinators.com. That'll at least explain the strength versus co-strength aspect a little better. It turns out that the co-strength path for deriving prisms isn't great because we don't have co-exponentials. Reed Barton built a, he was sort of the theoretical side of prisms. I derived them one way just from like reasoning about them in a fairly ad hoc manner. And he derived them from first principles, and we converged to the exact same definition, so we were pretty happy that we got the right answer. Kind of like how with lenses, we can derive the laws like 4 or 5 different ways, and they all come to the same laws. Oh, I have one more. Okay.
Now, scheme, core logic, snowball, and assembly in one lens.
All right. Well, thank you.